Okay, now when this radiation is released to make the nucleus more stable, there's no real way of predicting when any one nucleus is going to actually decay, but you can actually look at a pattern there, and there is a time for half of that total amount of initial radioactive substance to decay, and that's called the half-life. So let's say you had a radioactive sample that was made up of 10 kilograms of that sample. They will have found out as the half-life of that sample then, the time it takes for half of this to decay. So let's say it was actually, say, 1 hour. So what would happen then is in 1 hour's time, in 60 minutes, half of this should have decayed. So it should have dropped down 25 kilograms of the parent nucleus, the radioactive nucleus, and the rest of it would have actually become something else in the nuclear reaction. Okay. Now people then might think, oh, then another hour's time, then this would actually be gone, but that's not true, because now you've got a 1 hour period for half of this amount to decay. So half of that 5 kilograms will now decay, and you'll be down to 2.5 kilograms of the parent material, and so on. And again, you'll get more products there. And so then again, another hour, you get half of that, you get down to 1.25. So it goes through a process of having a full amount at the start, and then it has half of it after 1 half-life, a quarter of it after 2 half-lives, and then an eighth after 3 half-lives, and so on. It becomes a smaller and smaller fraction. So that would actually be the case for the mass of that, and also the number of nuclei that are in there that are radioactive would become half. So you could actually apply this to mass and the number of nuclei. But not only that, the activity, the amount of radiation it releases per second, will also go down. All right. Now the amount of counts you get per second from a sample is measured in becquerel, BQ, after Henri Becquerel. Okay. So that might have a count, for example, of say 60 becquerel, 60 counts per second to start with. Will it be as active as that when there's only half of the amount there? And the answer is no. When it's actually gone down to half the amount, you'll find the count goes down by a half as well, to only 30, and then the count goes down to 15. So they'll come down together in that same sort of exponential drop, if you like. Okay, so let's have a look at that. So as I said, it's impossible to predict when any one part of a substance will actually decay, but we can actually get an idea of the total number of nuclei steadily coming down over time, and that's the half-life. Okay, it is a random process, so it's not exact, by the way, from one measurement to the next, but it's an average. And you can find out how long it takes for half it to decay by looking at the activity coming down and graphing that, if you like. So that's the way you actually do it. The unit of activity of the substance is actually measured in becquerel, 1 decay per second. Alright, so here's a typical graph of the counts per minute coming down. You can see it starts at 80 up here, and then it's gone down to a very small amount. Now if you want to work out the half-life, we want to work out where half of the amount of the count's gone down to. So the half-life will occur when the count's gone down from 80 to 40, half its original count. So if you check that down and draw a line down here, it looks like it's around about 2 there. Okay? To reduce the size of the area, you would like to try it on a couple of half-lives or even 3 half-lives. So what you'll find is as the count drops from 40 to 20, that's another half-life that's gone through. That looks like it's kind of hitting around this 4 region here. So after 2 half-lives, it was worth a count of 20. That's probably going to indicate the half-life was actually 2 days. Okay? After 3 half-lives, the mass has dropped to 1/8. So you can see it goes from the full amount of 1 to a fraction of a half, to a fraction of a quarter, to a fraction of an eighth, and so on. And that will give you the half-life of this particular substance as you follow that exponential curve down there. It's possible for this time axis to be in any units, days, minutes, microseconds, years, and so on. Okay? Because there's a range of half-lives for all the different radioactive nuclei. So as I said, half is 1 half-life, a quarter will be 2 half-lives, an eighth is 3 half-lives, and you could do it as 1/2 to the end to work out the fraction that's remaining after n half-lives, okay? Some people do it a different way though if they're trying to work this process out. Now, so the things to be aware of here is that the half-life is not affected by the physical state or the chemical state of it, so it's independent of those states. So if you superheat this and try and melt it or change it to a gas, or ionise it, the physical state change is not going to change the nuclei's half-life. That affects the electron structure only. Okay? It's the same with chemical reactions. You can't suddenly blow it up with dynamite or whatever and change its state that way. It's all about the nucleus rather than the shell structure that's going on around it. Okay, let's just look at a couple of examples here of half-life calculations. So you have a 1 gram sample of carbon-14-6, and it's got an activity of 100 becquerel when it's 1 gram as a fresh sample, okay? They're told that carbon-14-6 has a half-life of about 5,570 years, and they want to know how long it will take for the activity to drop to 12.5 becquerel. So you really want to work about how much of a fraction has that gone down to. So I guess the few ways of doing this, you could start with your 100 becquerel account and say, look, that's 0 half-lives. Then you could say, okay, after 1 half-life, we've got a count of 50 becquerel, 2 half-lives 25, 3 half-lives 12.5, and we know therefore in step 1 you've got 3 half-lives. So that's normally your first step. Find out how many half-lives you've got involved in this question. So this is one way of doing it, just going down one step at a time. Okay. The other way of doing this is to go with, we've got 100 becquerel going down to 12.5. What fraction is that going to be? So it's 8 times smaller. In other words, it's 1/8. Now how do you get to 1/8? It's a half to the power of 3. Okay, gives you 1/8. So either of those two working outs there would show you why you've got 3 half-lives. Now having done that, it's easy enough to then work out how long it's going to take. So the next part of the process there would be, as a step 2, would be to go 3 half-lives times by the time for 1 half-life, and you get your answer in years. So you've got a mark there for your answer, a mark here for showing that you've got 3 half-lives there, I guess, and maybe wait for that working out somewhere. They're showing some working out there. Here's another one. You've got a sample of nitrogen 13-7 in the lab with a half-life of 600 seconds, and you're told how many nuclei it's got. You're told this differently now. How many nuclei will be left after 2,400 seconds? So this time you're told the time, and you're going to work out the fraction that's going to remain here. So if it's got a half-life of 600, and you've got 2,400 seconds that's going to elapse, how many half-lives is that? Well, you would just divide through as one method. So 2,400 divided by 600 is going to be 4 half-lives. So again, find the number of half-lives. So it's 4 half-lives. Now that means it's going to go from 1 to a half, to a quarter, to an eighth, to a 16th. Half to the power of 4. Okay? So we want 1/16th of this original set of nuclei here when you're doing this. Alright, so 4 lots of half-lives there. So you just need to do 1/16th of the original nuclei there. So you divided that by 16. You can see here the answer is 4.4 by 10 to the 15 nuclei atoms left over. Okay, so there's a few different ways of doing this, but finding the half-life first, the number of half-lives, normally is the way. You can also be asked to graph this. So this is why there's a time in minutes versus the counts per second. If you do graph this, the time always goes down the bottom, in this case in minutes, and you've got a crank right up the side. So you would try and draw this as a smooth exponential curve as a line of best fit. If that's 100 counts per second, then the half of that would be 50, and therefore that's your half-life is going to be somewhere in here, about 1.3 roughly. You could also try going half of that and going to 25, and coming across and seeing where that lines up, which is at about 2.5, just over 2.5 for 2 half-lives, which means 1 half-life is half of that. Okay, thank you for that.